Hi, I'm Professor Goins, and welcome to the Math Professor's YouTube channel. If you're looking for videos explaining topics in just about any college mathematics course, please consider subscribing, checking out our playlist, watching videos. Any liking, commenting, or sharing those videos or interactions, that would be greatly appreciated because it does help us to grow and reach a larger audience. Let's go ahead and get into the current video. I want to take a look at the topic of quotient spaces in the context of topology. And so first of all, let's say I've got a set consisting of a rectangle along with every point on the interior of that. So I've got this solid rectangular region. Now, suppose I was to define an equivalence relation on this so that I identify every point on this long edge with every point on this long edge, and I were to glue those together with an equivalence relation. Well, what happens here is I actually get a cylinder. Okay, so I get the cylinder. And now if I was to go back and say, well, now let's identify every point on the short edge, and let's just say those are equivalent, what happens is I take the cylinder and I'm going to take the circle that is on this side and the circle that is on this side, and I'm going to put those together, and I get a torus. Okay, so what I did is I started with this, let's say this rectangle, and then what I did is I defined an equivalence relation on it, and I come up with down here with which is the torus. And so this right here is a torus, which is going to be actually homeomorphic to the rectangle and modulo the equivalence relation. So the idea is that this torus is a quotient of the rectangle. Okay? A similar example, let's say I were to take a disk, and again this is going to be the circle along with everything on the inside, and so I take this disk, and then what I'm going to do is I'm going to define an equivalence relation on this so that every single point on the boundary, every single point on that circle is equivalent. So what happens is that this disk turns into a sphere. So the idea is if I was to basically take this and kind of like wrap it up, right, the boundary becomes a point at the top, and so therefore the sphere is homeomorphic to the disk modulo its boundary. And so both of these constructions here that I've got in the end after I kind of define this equivalence relation on it is a quotient of the original space, a quotient of the original set. And the idea is, well, what happens if these original sets had a topology? How could I then kind of inherit a topology on the quotient of the space? And that's what we want to take a look at in this section or in this video, is how, if I define an equivalence relation on a set, so I come up with a quotient of it, how does a topology factor into that? Pun intended with the factor, if you know factor spaces. So let me go ahead and give a definition here. So first and foremost, definition. Okay. So what I'm going to do is I'm going to say, for a topological space x tau, right? So that's sort of like this original rectangle or this original disk here. I've got this topological space, and define an equivalence relation say tilde on x. So again, I define an equivalence relation whether it was on the rectangle or whether it was on the disk. Then define a mapping, which traditionally is denoted by the letter pi. I'm going to take that from x to the quotient x mod tilde, right? So x modulo the equivalence relation by, well, the natural mapping from a set to its quotient would be a point is projected to its equivalence class. So I'm going to take an element and I'm going to map it to its equivalence class. And this is called the quotient mapping. All right. So now what I have is a function from the original set x to its quotient, and the idea is I want to figure out how can I then put a topology on this. Well, what I'm going to do is I'm going to define U is open in the quotient x mod tilde if and only if the preimage of U is open in X. And so we can see that that forces the quotient mapping to be continuous, which is kind of one of the basic types of a functions, and topology is continuous mapping, so naturally we would want the quotient mapping to be a continuous function. And defining it this way forces that function again to be continuous, which is going to allow me to then define a topology on the quotient. And you can verify this. I don't want to make the video super long, so I'm just going to kind of talk through this. This does actually define a topology on the quotient because the preimage preserves unions and intersections. So therefore the quotient topology, right, the topology that I just put on the quotient is in fact a topology. As I just mentioned, the open sets that I just defined on the quotient does in fact form a topology because preimages, the preimage of a union is the union of preimages, same thing with the intersection, so that the preimage preserves those operations. And so the collection of open sets just defined on the quotient x modulo tilde is called the quotient topology on x mod tilde, and so gives a quotient space, right? A set with a topology on it. So again, that gives me an inherited topology on the quotient from the original space. Well, let's look at a concrete example so we can kind of get an idea of what these open sets are going to look like. Let's take a look at the following. Let's say my set X is equal to the closed interval 0 to 1 with the, again, the usual topology. Usual topology from, say, your calculus course where open intervals are open. Open intervals form a basis for this topology. And let's define the equivalence relation tilde on X as follows. 0 is equivalent to 1, and for every x in the interior of 0 to 1, the equivalence class of x is just x itself. So everything in the interior is equivalent to only itself. The boundary points are equivalent to each other. And so what you could imagine is I take this closed interval from 0 to 1, and using this equivalence relation, again, what I'm doing is think of this as like a string. I'm taking 0 and 1 and making those equivalent, which means they're going to be in the same point. And what happens is I get a circle, so S1. Okay. So a quotient of that closed, bounded, in other words, compact interval 0 to 1 is actually homeomorphic to a circle. Well, let's talk about what the open sets would look like. First and foremost, let's say 0 to 1, those are going to be glued together, and then where is that over here? So let's say that is this particular point right there. So this right here is the equivalence class of 0 and 1. Now let's look at what do preimages of open sets look like. Well, if this is a subspace of the xy plane with the usual topology, and then this is again an open set here would be the intersection of an open set, say an open disk or something. So that means like I could have, let's say, open disk in the plane could look something like this, and then therefore an open set in the subspace, which is the circle, would consist of not those points on the circle, but then everything in between. So that right there, what I have just drawn on the circle, would say be an open set of that circle. Now, what would the preimage of that look like? Well, the preimage would look something like this. Okay, so it would be all the points, say, on the interior of that open interval, or that closed interval. Now, let's do another picture here. Let's pick an open set somewhere else. So 0 to 1, and then again, this is homeomorphic to the circle. Once again, let's identify where 0 and 1 get mapped to. Now, let's say I was to take an open disk, and it does something like this. So it goes around that point, which is equivalent to 0 and 1. Well, now my open subset of the circle is going to consist of that interval right there. What's the preimage? Well, the preimage is going to be the following. All right. It includes 0 and 1, and then also some points on either side of that, which would give me this portion of an interval, this portion of an interval. And notice that in the real line, this would be open in the subspace topology, right? It's the intersection of, say, two open intervals, intersected with 0 to 1, which would give me this portion, or this right here would also be open in the subspace topology as well. And so this kind of gives me an image of what do these open sets look like in the quotient topology, and how are they related to the original set X. I want to show you something that is within the context of a topological quotient space is going to be analogous to something from your group theory course called the fundamental homomorphism theorem. Let's say from group theory, suppose phi, which takes G to H, is a surjective group homomorphism. Now, this might not be, I'm gonna assume that it's not a, well, I mean, even if it is an isomorphism, the following will still be satisfied. But in the case where this is not an isomorphism, how can I create an isomorphism? In other words, what I have to do is I have to somehow get an injection from something related to G to H. Well, here's what I'm going to do. Remember, I have the following. I have G, which is a group, and I have that mapped into H via the function phi. And again, this is a surjection, so I'm going to put my little double arrow there again to indicate that it's a surjection. Well, for any group homomorphism, we can form the kernel of phi, and so what I can do is I can take G mod the kernel, which is a quotient group, and I can take the mapping from a group G to its quotient and I'll call that pi. So again, off to the side here, remember pi takes an element of the group and it spits out a coset of the kernel. Okay. So this is going to be also a surjection, right? And now what I can do is I can go from the quotient group to H, and what I'm going to do is I'll call this, let's say, phi bar, right? And the idea is that this now is going to be an isomorphism. So what happens is I know I've got this surjection through phi, and I've got this surjection from G mod to its G down to its quotient. Then what I'm going to do is I'm going to take a coset and I'm going to map it up to H as follows. So phi bar of, what I'm going to do, remember the elements of this are going to be cosets, so G kernel of phi. So what I'm going to do is I'm going to map that coset to phi of G. And the idea is that factoring through the quotient group actually sort of essentially filters out the portion of the mapping that's not injective and creates this commutative diagram where this in fact is an isomorphism. Okay? Said differently, if I have a surjective homomorphism from G to H, I can show that H is actually isomorphic to a quotient of G. Okay? Well, now what I'm going to do is I'm going to do the exact same thing, or an analogous thing, in the context of a topological space. Okay? So let's say, suppose f is a function from x to y. Okay, so f is this set function. So let's say is a surjective set mapping, and suppose y has topology. So the set y actually has a topology on it called tau y. All right. Well, then what I'm going to do is I'm going to define tau x. So in other words, I'm going to define a topology on x by, so what I'm going to do is I'm going to say V is an element of tau x. So V is an element of the topology on x if and only if V is equal to the pre-image. See what I used the function f, not pi. If and only if V is equal to the pre-image of U for some U in tau y. In particular, then, f is a continuous function. Okay? So now f is a continuous function, and finally I'm going to define an equivalence relation tilde on x by x is related to y, or x is, rather than, I guess you use the word related, x is equivalent to y if and only if f of x is equal to f of y. Now, of course, I ran out of screen here, so I'm going to have to go ahead and clean this side up. But before I do, what's going to happen, I'll leave this side up, I'll just clean up the group theory portion here. The idea is I'm going to come up with a relationship very similar to this diagram, where I've got x mapping to y, which is a surjective surjective mapping, which is continuous, and then I'm going to be able to show that y, the target space, is actually homeomorphic to a quotient of x. So let me go ahead and clean this side up, and then I will show you that. Okay. So with this in place, I'm going to say let f bar be a mapping from the quotient x modulo the equivalence relation to y be the function defined by f bar, which is going to take an equivalence class of a set, say, or an equivalence class of, say, x to f of x. Okay? So what I have is this mapping from a quotient of x to y. Then, here's the diagram that I have. I started with this mapping from x to y, okay, via the function f. Now what I have is a quotient of x, so x modulo the equivalence relation. And of course I've got the quotient mapping defined by pi, which takes an element of x to its equivalence class. What I just defined here was the induced function f bar. Okay. Now f is a surjective continuous function. Pi is going to be a surjection as well, and f bar, which takes an element of the quotient, which is an equivalence class, up to y, defined by f bar of x bar is equal to f of x. This is actually an injection. Not only that, it is also a surjection and is continuous, and its inverse is continuous. Therefore, this gives me not only a commutative diagram, but f bar, which takes the quotient of x to y, is a homeomorphism. So whether it's the context of group theory or topology, okay, and other subjects as well, if I have the sort of whatever function is related to those subjects, whether this is a continuous function in topology or a homomorphism in group theory, if this is not only has that property and is a surjection, then what I can show is that the image of that function is isomorphic, homeomorphic, again, whatever the case may be in that subject, is going to be equivalent to a quotient of the domain space. Okay? Anyway, I hope this gave you some indication of what a quotient space is in the context of topology. Please consider subscribing, and thank you for watching.